हाँ जी बेटा, अपनी नेक्स्ट कॉलिगेटिव प्रॉपर्टी थर्ड, डिप्रेशन इन फ्रीजिंग पॉइंट। Third colligative property, first two were relative lowering in vapor pressure and second was elevation in boiling point. What do you mean by colligative properties? The properties which are dependent only upon the number of solute particles but are independent of their nature. So third colligative property, depression in freezing point. Freezing point, what do you mean by freezing point? Freezing point of a solid is that temperature at which liquid and solid state have same vapor pressure. Boiling point is the property of any liquid and freezing point is the property of any solid. So freezing point of a solid is that temperature at which liquid and solid state have same vapor pressure. हाँ जी, so if we plot a graph, for example, this is vapor pressure and this is temperature. In the previous lecture, we have discussed the vapor pressure of pure solvent. Vapor pressure of a pure solvent is always greater than that of the vapor pressure of the solution. So, if A, B, C, D. So this higher curve is the vapor pressure of pure solvent, or you can say liquid, and this is the vapor pressure of solution. Because we know that when we add any non-volatile solute to any solvent, its vapor pressure gets lowered. That is called lowering in vapor pressure. That's why the curve of vapor pressure of solution is lower than that of the vapor pressure of the solvent. So this curve represents the pure liquid state. So let's suppose this is the temperature at which liquids start freezing, means it got converted into solid state. So this portion of the graph, for example, this is C, D and this is taken as E. So this CE, or we can say EC, represent the solid state of this pure solvent. So this temperature in which solid as well as liquid state have same vapor pressure. So this temperature is known as the freezing point of that very solid. So because it is a pure solvent, so we will denote it as T naught F. So this curve represents the vapor pressure of the solution. So if we want to freeze this solution, means this graph will touch to this solid state. For example, this is as dotted line. So this vapor pressure of the solution, this graph showing the vapor pressure of the solution, means it is in liquid state. When it starts freezing, then this temperature will correspond to its state when liquid as well as solid state has same vapor pressure. So this will be the temperature at which solutions start freezing. So this will be denoted as TF, freezing point of the solution. This temperature shows the freezing point of the pure solvent, and this temperature shows the freezing point of the solution. Means when we have added non-volatile solute to this very pure solvent. So from this graph it is very clear that T naught F is higher than that TF, or we can say after the addition of non-volatile solute its freezing point gets lowered. So lowered means depression. For example, in boiling point of the solution was higher. That is called elevation in boiling point. Elevation means increase and depression means decrease. So because the freezing point of solution gets lowered, so this is called depression in freezing point. So we can say T naught F is greater than TF. This T naught F means freezing point of pure solvent, and TF means freezing point of solution. Which solution? Which contains non-volatile solute. So if we want to calculate depression in freezing point, means we will denote it as delta TF. So delta TF will be equal to T naught F minus TF. In case of boiling point it was TB minus T naught B, but in case of depression in freezing point it is T naught F minus TF, because T naught F is higher than that of TF. So delta TF is equal to T naught F minus TF. This is called depression in freezing point. Again, experimentally it was noticed that this delta TF is directly proportional to the molality of the solution. So molality means, or we can say delta TF is equal to KF into M. So what is this KF? This is a constant. Which constant? Molar freezing point depression constant. In case of boiling point it was molar boiling point elevation constant, and this is molar freezing point depression constant, and its another name is cryoscopic constant. Which constant? Cryoscopic constant. So we have to define this KF. So delta TF is equal to KFM if M is equal to 1. Means again your solution is 1 molar, then delta TF will be equal to KF. So from this equation we can define KF. So what is the definition of this KF, or you can say cryoscopic constant? This KF or cryoscopic constant is equal to the depression in freezing point when the molality of solution is 1. ठीक है? So KF is equal to the depression in freezing point constant when the molality of solution is 1. Now similar to boiling point, if delta TF is dependent upon the molality, means it is again dependent on the number of moles of solute. So if it is dependent upon the numbers of solute, particles, then we can easily say that delta TF, or your depression in freezing point, is a colligative property. So we can say delta TF is dependent upon the molality, and molality is number of moles of solute dissolved per 1000 gram of the solvent. So it is again a colligative property. Now, similar to boiling point, we have to determine the value of MB, means molar mass of the solute, with the help of this expression. So, delta TF is equal to KF into M, or we can say delta TF is equal to KF into number of moles of solute divided by weight of solvent in grams multiplied by 1000. So this will be the value of delta TF, but number of moles of the solute, number of moles of the solute is equal to its mass upon molecular mass. So we can say delta TF is equal to KF into WB upon MB, number of moles of solute, and weight of solvent in grams means WA, multiply by 1000, or your MB will be equal to KF into WB upon delta TF into WA multiplied by 1000. So this will be your formula for the calculation of molar mass of the solute with the help of depression in freezing point constant, and this is again very important for your numericals. So this is the formula for the calculation of molar mass of the solute with the help of depression in freezing point constant. So we will solve one numerical. Numerical 45 gram of ethylene glycol So this is the formula, 45 gram of ethylene glycol is dissolved in 600 gram of water. Calculate freezing point depression and second, freezing point of the solution. We have to calculate two things. Freezing point depression. Freezing point depression means we have to calculate delta TF. Freezing point of solution means we have to calculate TF. So KF is given as KF is equal to 1.86 per mole. So this is the value of KF. So with the help of this formula we can calculate the value of delta TF. So solution delta TF will be equal to KF into WB into 1000 upon MB into WA. So KF, we have given the value of KF. WB means the weight of solute. Weight of solute means 45 gram of ethylene glycol. 1000 we have the value. Next is the molar mass of the solute. So we can calculate the molar mass of ethylene glycol. And second is WA, means weight of the solvent, that is 600 gram. Hanji, 600 gram. So first we have to calculate the value of MB, means molar mass of the solute. So formula of ethylene glycol is C2H6O2, means 2 into 12 plus 6 into 1 plus 2 into 16. 24 plus 6 plus 32, it will be 62. So we can calculate delta TF. KF 1.86, WB 45, multiply by 1000 divided by MB we have calculated as 62, WA means 600. So this is the weight of the solvent. So with the help of this formula we can calculate the value of delta TF, and its value comes out to be delta TF 2.25 Kelvin. 2.25 Kelvin. So next we have to calculate the value of TF. We know depression in freezing point is the freezing point of pure solvent minus freezing point of the solution, and we have to calculate the value of TF. So we can say delta TF minus T naught F will be equal to minus TF. ठीक है, तो डेल्टा TF means 2.25. ठीक है, so freezing point of the pure solvent, solvent is your, sorry बेटा यहाँ पे water है. So freezing point of the water is 0 degree Celsius. 0 degree Celsius means 273 Kelvin will be equal to minus TF. When we subtract, its value will be 270, approximately 270 if we take the exact value as 0.15. So this will be the value of freezing point of the solution, and minus will be cancelled. So TF will be 270.90 Kelvin. So this is the freezing point of solution. So by using this formula we can calculate the value of depression in freezing point as well as molar mass of the solute. So next is your last colligative property, that is your osmotic pressure. Hanji, what do you mean by osmosis? Osmosis is the flow of solvent particles across a semi-permeable membrane. Last colligative property is osmotic pressure. So before defining the osmotic pressure, we should know what is the meaning of osmosis. So what is osmosis? For discussing the osmosis, we will draw a diagram. For example, we have a vessel, and in this vessel we have taken pure water. So what is this? This is pure water, nothing is mixed in it. So this is your, simply we can say, solvent. In this water we have kept a funnel, inverted funnel. In labs you have seen the funnel. For example, this is your funnel. In this funnel, we have taken some solution. It can be sugar solution, salt solution, anything. Okay? This is exactly thistle funnel. This is known as thistle funnel, and thistle funnel, at the bottom we have attached some semi-permeable membrane. So this membrane is semi-permeable membrane. So what do you mean by semi-permeable? Semi means half, permeable means which allows the movement of some selected particles. So semi-permeable membrane means which allows the movement of some selected particles only. Selected particles in this case is solvent particles. So when we put this thistle funnel having a semi-permeable membrane into this water, what will we see? After some time, the level of solution in this funnel is increased. First, if we have to this much level, after some time the level of solution is increased. How does this level increase? So this is very simple. In this vessel we have pure solvent, and in this case we have solution. So solution, let it be sugar solution. So sugar solution means it has solute plus solvent. Solute means in this case sugar, solvent means water. So in this vessel the concentration of water is more as compared to the concentration of water in this funnel. So we know each liquid has a normal tendency to flow from its higher concentration to lower concentration. Means amount of solvent in the vessel is more as compared to the amount of solvent in this funnel. So water will move through this semi-permeable membrane to this funnel. So the level goes on increasing. So this movement of water from pure solvent to the solution side is known as osmosis. So it is so we can define osmosis as it is the movement of solvent particles across a semi-permeable membrane from pure solvent to solution. So how can we define the osmosis? It is movement of solvent particles across a semi-permeable membrane from pure solvent to solutions. So after some time the level of solution will rise. So this is what do you mean by osmosis? So after some time the level becomes constant. It is because of the hydrostatic pressure which will be exerted on the solution. Hydrostatic pressure, hydro means water. As the level of water in this funnel goes on increasing, this water will exert some pressure on this solution. So this pressure is known as hydrostatic pressure. So this hydrostatic pressure is a measure of the osmotic pressure. So how can we define the osmotic pressure? So this osmotic pressure is the equilibrium. So what do you mean by osmotic pressure? The equilibrium hydrostatic pressure, the equilibrium hydrostatic pressure on the solution which is exerted by due to the movement of pure solvent into it is known as osmotic pressure. So what is osmotic pressure? When the level of water in the solution goes on increasing, after some time we will notice that this level becomes constant, means this is your equilibrium state. So what is this equilibrium state denotes? It is the pressure, equilibrium hydrostatic pressure, which is exerted on the solution by the movement of solvent into it is known as osmotic pressure. So next, what do you mean by semi-permeable? Semi-permeable membrane means which allows the movement of some selected particles, or you can say solvent particles only. In nature there are some semi-permeable membranes. For example, plants and animals have some membranes which are semi-permeable in nature. Pig's bladder, for example, pig's bladder is the common example of semi-permeable membrane. In addition to this, there are some man-made semi-permeable membranes also. For example, this is your natural semi-permeable membrane. Man-made best example is cupric, ferrocyanide membrane. So these are the example of your semi-permeable membranes. We can easily show osmosis in labs also. Bio students, maybe they have done this experiment in +1. Osmosis, for example, we have two vessels. In one vessel we have taken pure water, and in second vessel we have taken salt solution. Salt solution in which salt is in large amount. Large amount means some excess amount, not more than water. Okay? So this is your pure water, this is your salt solution. If we place egg into these solutions, we have put 2 eggs, but eggs whose outer shells are removed. Okay? So now this layer of egg will act as a semi-permeable membrane. Now in this case, egg has some material inside it means some type of solution. So inside the egg there is some solution, and outside the egg there is pure water. So water will move from vessel towards egg. And what will we notice? After some time, egg will swallow. Egg will swallow means egg will swollen. So what does means? Water has entered inside the egg. So that's why this egg swells up. Swells up means फूल जाना, पहले से size में बढ़ना. So this egg will be now in swollen state. So this egg will be in swollen state. So this is because of osmosis. But in this case, in which we have put egg in a much concentrated salt solution. So in this case, the solution inside the egg will move outwards. So this outward arrow means solution inside the egg is moving outside the vessel. So after some time, this egg will shrink in size. Shrink means lesser in size. So these two processes are simply osmosis. Osmosis means movement of water or any solvent from its higher concentration to the lower concentration. But in this case, the concentration of water inside the egg is more as compared to the amount of water in the vessel. So in this case, water will move outwards, so egg will shrink. But in this case, water will move from the vessel towards the egg, so this will swell up. Okay, so these two processes are osmosis. So next important question is, what is the difference between osmosis and diffusion? So diffusion means simply the movement of any particle from its higher concentration to lower concentration. But in osmosis, we are talking about only the movement of solvent particles. Second main difference, osmosis always requires a semi-permeable membrane, but in case of diffusion there is no such requirement, means no semi-permeable membrane is required in case of diffusion. Third main difference, osmotic pressure is applied only for the liquid solution, but diffusion can be applied to gases as well as liquid. So these are three main differences between the osmosis and diffusion. So next is, how will you show that osmotic pressure is a colligative property? So we denote osmotic pressure by a term known as pi, and experimentally it is found that pi is equal to CRT. So what does this mean? C means concentration of solution. This R is gas constant, and this T denotes temperature. And we know the gas constant is a constant and temperature for a particular process is also constant. So pi is dependent upon C. C means concentration, and concentration, but concentration means number of moles per liter volume. So pi can be written as N upon V into RT. So pi is dependent upon the number of moles. So again it is a colligative property. So pi is dependent upon the number of moles of of solute particles, so it is a colligative property. So this is a colligative property. Now next, calculation of molar mass of the solute with the help of this formula. So pi is equal to N upon V RT, but N means number of moles. It is again equal to WB upon MB. So we can write pi as WB upon MB into V RT, or MB is equal to WB upon pi into V R into T. So this is the formula for the calculation of molar mass of the solute with the help of osmotic pressure. So pi is dependent upon the concentration. Concentration means number of moles per liter volume, because it is dependent upon the number of moles. So pi is again dependent upon the number of moles. So if it depends upon the number of moles of the solute, so we can easily say that pi means osmotic pressure is a colligative property. So this number of moles is equal to mass upon molar mass, that is WB upon MB. So with the help of this formula we can calculate the molar mass of the solute with the help of the value of osmotic pressure. So we have done all the colligative properties. What are the colligative properties? First was relative lowering in vapor pressure, second was elevation in boiling point, third is depression in freezing point, and fourth is osmotic pressure. You have to learn all these four formulas very seriously, because they are very important for your exams from the numerical point of view. So in the next lecture we will discuss 1-2 numericals related to osmotic pressure and biological importance of osmosis, as well as our last topic, that is Van 't Hoff factor. So in the next lecture our solution chapter will be completed.